A word problem on proportions. The residents of a city voted on whether to raise property taxes. The ratio of yes votes to no votes was 3 to 2. If there were 2,685 total votes, how many yes votes were there? Let's write out some ratios. And so we could have 3 yeses to 2 no's. And we want to know how many yeses are there. So let's say X is the number of yes votes out of what? Out of a total of 2,685 votes. So how many no votes are there? Well, the no votes must be 2,685 subtract the yes votes. And so we get a nice equation here called a proportion. And a proportion is basically a fraction equal to another fraction. And of course, we could solve this. We do need to multiply 3 times 2,685. So when you solve this, I guess the most consistent way of doing this is actually clearing the fractions with what we call fraction busters. So we go 2 times 2,685 minus x. So we're going to multiply by the lowest common or least common multiple of the denominators. And then over here we can multiply by the same quantity, 2,685 minus x. And the next line will give you an equivalent equation, which will give you 3 times 2,685 minus x is now equal to 2x, or 2 times x. Let's solve this. So we got 8,055 minus 3x is equal to 2x. So 5x is now equal to 8,055, and we could divide by 5. So let's divide the entire sides by 5 because 5 is not 0, and let's see what we get. X is equal to, let's see here, that shouldn't be too bad. 8055 515 051 and 5, and then we get 0, bring down, and we get another 1, so we got 1611. Now, we need to write your answer in a complete sentence. There were, how many yes votes? 1,611 yes votes. Don't forget the vote. All right. Find the length x. Question number 2. We're supposed to see similar triangles. I guess I could say 1 here and then put 2 here. Questions 1 and 2. We're supposed to see similar triangles down below. And so with geometry, a nice little trick is to actually redraw the problem. We want to separate the puzzle. So x here and the hypotenuse here is 6.5. And then we could, draw the bigger piece. So there's a small piece and a big piece. And this one's 9. And this one is, the hypotenuse is now 13. So with similar triangles, you just have to set up a ratio that's equal to another ratio. So just be very, very consistent with this. So I'm going to go this way. So x is to 9 as 6.5 is to 13. So we can multiply the entire sides by 9 and 13, 9 times 13. And we get what? We get 13x is now equal to 6.5, which is what? 13 halves times 9. And we want to divide the entire sides by 13. So we get x is now equal to 13 times 9 over 2. Divide by 13 means multiply by 1 over 13. So the 13s are going to cancel, and you're left with x is equal to 9 over 2. So the missing length has 4.5, right? I guess you could put it back in 4.5. 4.5 what? 4.5 units of length. The units were not given to us, but clearly it's measuring some kind of distance, and that distance here is called length. Let's circle our final answer. Let's solve this equation here. I'm going to rewrite it so it's nice and big. 3 times y to the negative 1/6 power is equal to 6. The first thing you want to see is that there is an invisible multiplication there. And so we want to isolate y as much as we can by itself. Since 3 is not 0, we could divide the entire sides by 3, and we get y to the opposite of 1/6 is now equal to 2. Now, how do we get y by itself? Well, we could use exponents. So y to the negative 1/6, and we'll use an exponent here of negative 6 is now equal to 2 raised to the exponent of negative 6. The power exponent property is what? Y to the p raised to the m is simply y to the p times m. So a power to the power rule of exponents with a base of y. So what are we writing next? Y here is equal to, or y to the first power, which is just y, is equal to 2 to the opposite of 6. And what is 2 to the opposite of 6? Remember, that is just a reciprocal. 1 over 2 raised to the 6th power. And then therefore, y is equal to 1 over 64. Remember, a to the opposite of n is simply says, take the reciprocal of a and raise it to the n. Or you can remember this formula. Some of you will remember that it's 1 over a to the n. So that's a little bit more of a shortcut. So either one of those is fine. In this case, y is simply 1 over 64. Now, is this problem about expressions or equations? And so if you go back and look at all your writing, make sure you understand what you're writing. You wrote an equation, you balance that equation. So you wrote another equation, and then you wrote another equation, and then you wrote another equation. And even your answer is an equation. So throughout this process here, you are writing equations. Let's go ahead and graph this function. Ironically, it tells you a function, but it doesn't use function notation. So why don't I write in the function notation for practice? So a function, remember, is f of x, and then it's equal to negative 7/4 times x to the third. Let's see. Well, you know your parent function is this. I mean, you know x cubed, that function is shaped like that in the Cartesian plane. So the opposite of x cubed is going to reflect across the x-axis, and it will actually shape like that. But why don't we actually pick ordered pairs? If you're not really sure what the graph looks like, you could always just pick ordered pairs and make a t-chart, label your ordered pairs. I recommend here, do 3 to 3 to 5 coordinates, to get used to it, get used to the graphing. Remember, it is a function. It's a polynomial, so make sure you put arrows at the end to match the domain and range. Why don't we get started? I do need some graph paper, so you guys could draw your own graph paper, I guess. Why don't I use this color? Then so we have a set of axes there, and this is going to be a rather steep x to the third power, because the coefficient is more than 1, or the magnitude of the coefficient is more than 1. In fact, it's almost about 2. So it's going to make this curve a little bit steep. It's going to increase really, really rapidly or decrease really, really rapidly. Let's get a t-chart going. So the t-chart here is simply x and f of x. And f of x here represents the y value. Why don't we just keep things a little simple? Why don't we try -2? And if you try -2 and evaluate it, what is f of -2? -7/4, put parentheses -2, raise it to the third power. So we got -7/4 multiplied to -8. So we got 14, right? So that will get you 14. -1, you get +7/4. 0, you get 0. And then we get a nice symmetry going on. If you put 1, we get -7/4. And if you put 2, you end up getting -14. Another thing I'm going to do now, since I'm using my own graph paper, I'm going to do this not to scale, just to save a little bit of time. I'm going to draw this not to scale. So I will draw, let's say, 3 units this way. And what do I mean by not to scale? Well, I'm going to probably draw the, let's call that 20. Cut that in half, we call it what? 10. Cut that in half again, we call it 5, right? I'll count -5, -10, and then -15, and so on. That's good. Now let's plot our ordered pairs. -2 and 14 is right about probably here, a little bit less than 15. So if I wanted to, I should probably put a mark here, say that's 15. And then -1 and 7/4, well, it's almost 2. So -1 and 7/4 is almost 2. 2.5 is here, about here. And then 0, 0, it goes through the origin. And then we draw a similar pattern once we go to 1. And then when we go to 2, we get to -14. And then play connect the dots. It's a nice decreasing function from left to right, with the domain to be what? -infinity to infinity, and with the range to be -infinity to infinity as well. So when you're graphing, when in doubt, just get some accurate ordered pairs and then draw your graph. Now, I'm a little off there. I forgot to connect that red dot, so I'm going to cheat a little bit by making that bigger. So here is a picture that represents a function because it passes the vertical line test. Okay, we're actually looking at the function called g of x. And so you can call this y-axis to be g of x, because g of x represents the y value. We're asked to find the domain and range. And so remember that the domain is the set of all possible input values. So the domain is the set, or I should say interval, of input values. And what are input values? They're usually the x values. Well, they are the x values. Sometimes they're the values called values represented by the independent variable. Why don't we find that? Why don't we find a domain? And the way you read domain is sort of look left and right. We'll start really far left. And so I'm actually going to draw here. So there are x values right here throughout the function, and if it doesn't include -3. So that goes to -5 up to -3. And then we got to include another interval, or we union another interval. And so we're going to union parentheses -2, and then all the way up to what? All the way up to bracket 5. So let's write that. And I use sort of an advanced notation to represent domain. I usually use DOM parenthesis of G. And the way you read this is the domain of G. So this is the domain of G. And this is the notation that my engineering students get to use, or my students in differential equations get to use. And I'll let you guys use this as well. So the domain of G, well, we've written it, and you just got to write it in interval notation from left to right. So -5, parentheses 3, parentheses -3, union, joining, union meaning joining, parentheses -2, comma, up to 5, and then we include 5, and we symbolize that with a bracket. So a bracket means include. So we got the domain. Now, why don't we find the range? And the range here, well, instead of reading left to right, we're going to read from bottom to top. So what is the first y value that shows up on the bottom? Well, the first y value shows up right about here, but it doesn't include -4. So it shows up here. And then we're reading now from bottom to top. So if it helps, maybe you rotate your head 90 degrees to your right. So you're just turning the paper, and then you got to see the y values, or the g of x values, and then you got to just figure out when do the y values stop. The y values are going to stop here. And once again, parentheses, and we don't include 3. So why don't we write the range of G? The range of G is the set of all output values, or the set of all y values that are possible on your graph. So in this case, the range is simply from -4, comma, up to 3. And there you go. The range is the set or interval of output values, or y values. Okay. Why don't we graph this equation in a Cartesian plane? And remember, the absolute value plays the role of parentheses in your order of operations. Okay, but it also means take the absolute value. So we'll write out some of these computations. The best way to graph something, especially if you're unsure, is simply pick some ordered pairs. And why don't we pick some ordered pairs from, let's say, -4, -3, -2, and so on. Oh, actually, before I pick -4, why don't we go take a step back and look at the basic function. And what do I mean by basic function? Well, we should know how to graph this, right? So if I made a t-chart for x, f of x, -2, what's the absolute value of -2? It will be 2. -1 will be 1, 0, 0, and then 1, 1, and then the absolute value of 2 is 2. So this actually, you got to remember, this actually graphs a what? If you put those ordered pairs, 1, 1, 2, 2, it actually graphs a piecewise function in two pieces. So you have a straight line going this way, Why don't I draw this in a different color? How about that? Make sure you put the arrows because you got to match the domain and range. Okay, make sure when you're graphing, draw your arrows to match the domain and range. Don't forget that. And so that is our basic function for an absolute value. So why don't we graph, let's say, this function over here. We can call this g of x. And let's pick on some values. What values should we pick? I'm going to pick, what did I say, -4, -3, -2, -1, and 0. Maybe even pick 1. Let's see what happens here. Let's look at g of -4. What is g of -4? It's an expression, so it's going to equal what? -6 times the absolute value of -4 plus 2. Now the absolute value acts as parentheses. So we go -6. So we got to do inside the absolute value first. So that would be absolute value of -2. That says -6 times the absolute value of -2. So -6 times now +2 because we took its absolute value. So we get -12. So at -4, the y value, the output value is -12. In a similar fashion, we can get all the other output values. So if you put in -3 right here, put -3 in here, you get the absolute value of -1, which is 1, and then 1 times -6 is -6. We get 0 here, that's nice. And then we get a 1 times -6, so we get -6. 0, 2, -12. And then what happens at 1? We get -18. Okay, I think that's enough ordered pairs to get this going. So maybe we use a scale of 6 for the y-axis. We use a scale of 6 for the y-axis here. So this isn't going to be perfectly the scale. So let's draw it. Let's say it's not the scale. And we have an x and we have a y. And over here I could go 1, 2, 3, 4, -1, -2, -3, -4. And let's draw our y values on a scale of 6. So I'm going to go 1, 2, these are 18, this is 12, and then this is 6. This is -6, -12, and -18. And let's plot some ordered pairs. So it's the shape of a V, but is it right side up or is it upside down? I'm convinced it does this. So make sure you draw your arrows so that it matches your domain and range of the function. Don't forget your arrows. And so make sure you always draw your graphs on your own separately. Okay, it's good to label your ordered pairs. You could label your ordered pairs in a T-chart. So why don't we circle those? So there's some ordered pairs, and of course there's your graph. Oop. Let's try to graph this square root function. And if you're ever unsure about graphing, it's always good to just put some input values in here and see what the output values do. You know, it's always good to just pick some ordered pairs or try to get a hold of some ordered pairs. However, I am going to find a domain of this square root function. And you got to remember the basic function. You know, you got to recall the basic function that you learned in a previous algebra course. So g of x is equal to square root of x. And, you know, what does that function look like? I mean, quickly, you can see that, you know, it starts at 0, 0, and then it goes up to 1, 1. But then when it goes to 4, it bends its way to the output value of 2, and then of course when you get to 5, 6, 7, 8, 9, it bends the output value to what? Bends its output value to 3. So it's half a parabolic branch in pointing towards the y direction. I mean, not the y direction, sort of running parallel to the x-axis, but it's not. It's actually increasing. It is an increasing function from left to right. So that is our basic square root function. Notice the domain here of g. Let's see, domain of g here. Now, in a total surprise, it's actually 0 to infinity, right? Because you simply take the x and make it greater than or equal to 0. We're going to do the same thing here. We're going to take this 1/2 x plus 5 and make this greater than or equal to 0 to find a domain. Multiply the entire inequality by 2, and we get x plus 10 is greater than or equal to 0. X, in fact, is greater than or equal to negative 10. What does that mean? What is the domain of f? It is simply going to be the interval, bracket, negative 10, all the way to infinity. Now we just want to pick some ordered pairs. Why don't we get a hold of some ordered pairs? If you have graph paper, always comes in handy. And then, of course, if you have a straight edge of some sort, maybe your scientific calculator could be your straight edge, or the edge of your binder. But you want to have, something to draw a straight line with. So there's a pair of axes there. This is the x direction. This right here is the f of x direction. And we need some ordered pairs. So we should pick what? Negative 10 is included. Let's pick negative 10. What happens at negative 10? Well, it's kind of convenient. We get negative 5 plus 5, which is 0, and the square root of 0 is 0. Okay? Now, I'm actually going to pick something else. I'm actually going to pick, let's say, what should I pick? I think negative 8 would be good. What happens when you pick negative 8? Pick x to be negative 8. Nice and convenient. If you pick x to be negative 8, we get negative 4 plus 5, which is 1. And what's the square root of 1? The square root of 1 is 1. Whoa! What else can I pick? Strategically, what do I want to pick? I think I want to pick negative 2 next. Pick x to be negative 2. What is x to be negative 2 going to do? X to be negative 2, we get negative 1. Negative 1 plus 5. What's negative 1 plus 5? You get 4. But what's the square root of 4? It is 2. All right, we're good. Let's plot these ordered pairs. I guess I could draw this to scale. And then we have 1, 2, 3. Do the best you can there. You might have your own graph paper. That always helps. And there we go. It sort of looks like, your square root function. But this square root function is shifted to the left 10 units. And it's also, it doesn't have that height like your g of x does up there. But there you go. You got the domain of f, you got your t-chart, you got a nice graph with a few ordered pairs that are labeled. Make sure you draw the arrow at the end of your graph so that it matches your domain and range. And so these should match, right? Let's go ahead and factor this polynomial, knowing that negative 3 here and 3 are zeros. Well, if negative 3 and 3 are zeros, by the factor theorem, you know that let's see here. We know that x plus 3 is a factor. And we also know x minus 3 is a factor. So this one here and this one here, they correspond like that. Those are both factors. They're both factors of who? They're both factors of the polynomial f of x. So why don't we use synthetic division and divide this polynomial by x plus 3 as quick as we can? And remember, synthetic division only works with a monic binomial, which is what we have. X plus 3 is a monic binomial. We do need the coefficients. The coefficients are what? 1, 4, negative 10, negative 36, and 9. Now you got to remember, with synthetic division, the first thing you do is bring down the 1. And then we are going to multiply 1 times negative 3, add it to 4. 1 times negative 3 is negative 3, add it to 4, which is 1. Write the 1 here. Repeat this process over and over again until you finish the division. So 1 times negative 3 is negative 3, added to negative 10, we get negative 13. Negative 13 goes here. We do the same process to negative 13. Negative 13 added to negative 3 is positive 39. Positive 39 added to negative 36 is 3. And then 3 times what? 3 times negative 9 is negative 9 added to 0. And not a total surprise, we get a remainder of 0. Or maybe I'll color code it with that. We get a remainder of 0 here. Well, shoot, we kind of knew that already because by the factor theorem, f of 3 will yield that remainder of 0. Aha! More importantly, well, what have you just shown? You've shown that you could rewrite f of x. In fact, f of x is what? We have parentheses x plus 3, and then you divided, so you divided by x plus 3, and that means the rest of the polynomial would have 1 degree less. So we actually have x to the third plus an x squared minus 13x plus 3. Aha! And of course, we repeat this process, knowing that knowing that positive 3 is a 0. We're now going to do synthetic division to the third degree polynomial. And we repeat this by bringing down the 1. And we're doing synthetic division again. And it goes pretty quick. Not a total surprise. You once again get a remainder of 0. And once again, you rewrote f of x to be something nice. You rewrote f of x to be x plus 3. And now it is x times x minus 3. And then what is left over? X squared plus 4x minus 1. And now we just got to factor that last quadratic expression. And how do we do that? Well, the way we do that is, well, let's see if we could find the rest of the zeros. If we could find the rest of the zeros, then we're in good shape. So why don't we consider this? Off to the side here, consider x squared plus 4x minus 1 to be equal to 0. We want to find the rest of the zeros. And this doesn't factor. I mean, you could try the trial and check method, you could try the AC method. This does not factor easily, so we're going to apply the quadratic formula. X is equal to the opposite of b, plus or minus the square root of b squared minus 4ac, all over 2a, which I know you gladly remembered. And, you don't have to tattoo it to your body, but you should try to remember that and memorize that. Now, let's evaluate. X is the opposite of 4, plus or minus the square root of 4 squared minus 4 times 1 times negative 1, all over 2 times 1. And we get x is equal to negative 4 plus or minus 16 plus 4, well, that's just 20, and divided by 2. X is equal to, I'm seeing a common factor pretty soon, so I'm going to factor out a 2. And we have, what's left? I see a negative 2 plus or minus. It was 2 root 10. So if it was 2 root 10, then I only have a root 10 left. And then put that all over 2. This 2. And of course we know 2 over 2 is 1. Okay, you could reduce those factors. Now, how do we write our linear factors? F of x is equal to, let me write that a little bit higher. I'm starting to realize I'm running out of room. So I'm going to write that a little bit higher. And we have an x plus 3 as a factor, as a linear factor. We also have an x minus 3 as a linear factor. The next one was a quadratic factor. We're going to break that into 2 linear factors as well. So we're going to write x minus, in parentheses, negative 2 plus root 10. Put another parenthesis. Then we write x minus, parentheses, negative 2 minus root 10, parentheses, parentheses. Now, one more simplification, and it will look very nice and pretty. You know, the muscles in your hand are getting stronger. It is really muscle memory after a while. And there you go. You've written the polynomial f of x into 4 linear factors, with 2 of them being real zeros and 2 of them being complex zeros. You got to remember, complex zeros always come in conjugate pairs. Use the conjugate zeros theorem to find all zeros of a polynomial. So here's a polynomial, and you're given one of the complex zeros. Negative 3 plus 2i is a 0. What does that mean? Well, that means you get 2 things. One of the things is that you get x minus a negative 3 plus 2i is actually a factor of the polynomial. And you also get what? You also get x minus a negative 3 minus 2i is a factor to that polynomial. What happens when you multiply these together? Well, we do a little bit of trickery here. We are actually going to reassociate this by saying this is going to be x plus 3 minus 2i, then multiply by what? We want, let's say, x plus 3 plus 2i. So now we have a difference of 2 squares. And this is going to get you a very, very nice quadratic expression. In fact, it will get you x squared plus 6x plus 9 minus 4i squared. So if you do minus 4i squared, that really just means add 4. So if you add 4 to that, we get 13. Now we want to find the other zeros of this polynomial. So what we're going to do now is take long division and try to take that divisor and see if we could divide it into x cubed plus 3x squared minus 5x minus 39. And of course we can. We just need an x to get this going. What do we get now? We got x cubed plus 6x squared plus 13x, and then we are going to subtract and we get negative 18x and then you could bring down and we get negative 39. Oh, I caught a mistake. So that should be what here? There should be a negative 3x squared here. And that looks way better because now I could write what? Minus 3, or subtract 3, and we get negative 3x squared minus 18x minus 39, and when you subtract this, we should get a 0 remainder, and we do. Very nice. Nice finish line there. All right. Okay. So we got an x minus 3. And that means we have, oh, that means we're done, because this is a degree 3 polynomial. So we just need to find all the zeros. P of x is now equal to what? X minus 3 times what? That quadratic, which is x squared plus 6x plus 13. But we already know all the zeros. We just need to list them. The zeros are 3, negative 3 plus 2i, and negative 3 minus 2i. Let's find all the horizontal and vertical asymptotes of a rational function. And there's different cases, different scenarios. You could have a quadratic numerator or a quadratic denominator. And what we're going to do is, for the rational functions, we're going to compare degrees of the numerator and the degrees of the denominator. So for example A here, f of x is equal to 8 over x squared plus 9. Well, the degree of the polynomial of 8 is actually 0. And so if we look at the degree of the numerator is 0. Okay, the degree of the polynomial in the numerator is 0. But what's the degree of the denominator? The degree of the denominator, or the degree of the polynomial in the denominator, is 2. Now, in this case, we have the degree of the numerator is less than the degree of the denominator. That's going to imply that we have a horizontal asymptote of y equals 0. And x squared plus 9 is never going to equal 0. So we don't have to worry about that denominator. We don't have any vertical asymptotes. So no vertical asymptotes at all. So no VAs. Okay. So we have no VAs. We have a horizontal asymptote of y equals 0. Why don't we graph that? Horizontal asymptote of y equals 0. So remember, this is your x, this is your y. The horizontal asymptote could be represented by y equals 0. It's actually this dotted line right here. In fact, another name for y equals 0 is simply the x-axis. So there it is. You could label that dotted line, horizontal dotted line, to be y equals 0. Let's look at example B. Let's find the vertical and horizontal asymptotes of this function. This time the degree of the numerator is 2 and the degree of the denominator is 1. So if that happens, the degree of the numerator is 2, which is greater than the degree of the denominator, which is what? Which is 1. This implies, these two conditions imply that we do not have a horizontal asymptote. So no horizontal asymptote. In fact, if you do some long division, you will discover something quite different. No horizontal asymptote here. But do we have any vertical asymptotes? Yeah. I mean, to find a vertical asymptote, we already know that 2x minus 5 can't be 0. So x cannot be 5 halves. Turns out it cannot be 5 halves. Well, that actually will help you yield that the vertical asymptote is x equals 5 halves. So we have a nice little wall here. So about 2, 3, and x equals 5 halves is what? Well, x equals 5 halves is right there, right between 2 and 3. So make sure you draw the little arrows on your vertical asymptotes. You have to draw that yourself. You know, take a sheet of paper or a sheet of graph paper and make sure you draw your arrows at the end of your straight lines. What about the last example here? What if the degree of the numerator and the degree of the denominator is the same? Well, that's also yielding very, very interesting results. So if you continue to study calculus, you're going to realize that the degree of the numerator equaling to the degree of the denominator, something magical happens, and that is, if that happens, you do get a what? You do get a horizontal asymptote. And in fact, it's actually just going to be the coefficients of the highest, the coefficients of the term with the highest degree. So in this case, the horizontal asymptote is y equals negative 3 over 1, and of course that means y equals negative 3. Are there any vertical asymptotes? Yes, yes, yes. Vertical asymptotes, we could find those as well. And the way we do that is make sure that the denominator is not 0. But this has a nice pattern, in fact, with factors. So we have what? X cannot be negative 1, and x cannot be negative 2. But together, that yields 2 vertical asymptotes. The 2 vertical asymptotes are x equals negative 1 and x equals negative 2. I'll leave it up to you to graph those. Remember, this one is horizontal. Well, shoot, they're already labeled. They have HA here, okay? So, you guys will draw those yourselves. Why don't I circle my answers? We got a no horizontal asymptote in example B, and we have a vertical asymptote in example B. We have 2 vertical examples. We have 2 vertical asymptotes in example C, and we have 1 horizontal asymptote in example C. There we go.